Hey everybody, welcome back to another calculus video. So, we've talked about what happens to a function when it's increasing and decreasing and how that's connected to the sign of the first derivative, right? If a function's first derivative is positive, then the function's increasing. If a function's first derivative is negative, then the function is decreasing. And so we ask the question, okay, can we make any similar statements about maybe f prime, the first derivative, and connect that to the second derivative? Okay, yeah, we can talk about the first derivative increasing and decreasing, but does the second derivative give us anything more, specifically about our original function? Let's look at a couple pictures. Maybe one picture where we have a function f that looks like this. Maybe another where we have a function f that looks like this. These are both increasing functions, right? They both have positive first derivatives all the way through. But let's look at what happens to the first derivative as we move from left to right. So on this one over here, kind of a flatter first derivative. Then it gets kind of more steep, rather flatter tangent line, then more steep tangent line. And then all the way up here, we have a really steep tangent line to the graph of the function. So the tangent lines seem to be getting steeper and steeper and steeper. In other words, f prime is increasing. Because the first derivative measures the slope of those tangent lines, so if the slope is getting steeper and steeper and steeper, it means that f prime is going up. But how about this one? The function is still increasing, but the tangent lines go from being very steep to less steep to actually kind of flat. It's the opposite of the first picture. In this case, f prime is decreasing. And we see that corresponds directly to the shape of the original function. When f prime is increasing, it's almost like f is bending upwards. And when f prime is decreasing, it's almost like f is bending downwards. Well, let's quantify that mathematically. Definition, let f be a differentiable function on the open interval a to b. Alright, so we have a function where we can start talking about the derivative for it. Then we say that the graph of f is concave upwards. If f prime is increasing on a to b and concave downwards if f prime is decreasing on a to b. So, key note, both of these functions are increasing functions, but because f prime is increasing here and f prime is decreasing here, this function is concave upwards, this one is concave downwards. Alright, so that's a cool definition and all, but how does that connect to the second derivative? Well, if we're talking about whether f prime is increasing or decreasing, then we need to talk about the derivative of f prime in order to find regions where it's increasing or decreasing, assuming the function is twice differentiable. AKA, to find out information about f prime increasing or decreasing, we use f double prime. Of course, this is assuming that our original function is twice differentiable. Right? If the second derivative doesn't exist, this kind of analysis doesn't make sense. But thankfully for us, a lot of the functions we've been dealing with are twice differentiable, so we can use this just fine. Theorem. It's actually a direct corollary of the theorem we have about when a function is increasing or decreasing. If f double prime of x is greater than 0 for all x in a to b, then the graph of f is concave upwards. On a to b. Makes sense, right? F double prime of x greater than 0 means f prime is increasing, which is the definition of concave upwards. And we get the exact same thing for concave downwards. If f double prime of x is less than 0 for all x in a to b, same thing as above except concave downwards. On a to b. Okay, makes sense. So, how do we find intervals of concavity for our function? Well, let's just adapt the process we used for showing whether a function is increasing or decreasing and apply it directly to the derivative. So, to find intervals of concavity. If f double prime exists. Step 1, we'll need to actually compute the second derivative. And then we'll set equal to 0 in order to divide the number line up into intervals, just like we did for the first derivative. So, find x such that f double prime of x is 0 or undefined. And then split the number line into intervals. Then finally, we'll use test points to determine the sign of f double prime of x on those intervals. Alright, so, pretty nifty, nice process because it's very similar to what we've been doing with the first derivative. And that's always good when things build on each other like that. So, let's do an example. Maybe even 2. Alright, example 1. Let's determine where f of x equal to 3x cubed minus 4x squared plus 7x minus 4 is concave upwards and downwards. Alright, well, to do that, according to this process here, we should start by computing the second derivative. To get to the second derivative, we compute the first derivative first. And f prime of x in this case would give us 3 times 3, 9x squared minus 2 times 4, 8x to the first, aka just 8x, plus 7, and then the minus 4 gets dropped when we take the derivative. Okay, so that's f prime of x, but now we need f double prime of x, so let's take the derivative again. That'll give us 18x minus 8. And then, again, derivative of 7 is just 0, so that goes away. Alright, so we have step 1. We've computed f double prime of x. Step 2, we need to solve for where f double prime of x is 0 or is undefined. This is a polynomial, so it's defined everywhere. We don't have to worry about that second condition. Let's just solve when it's equal to 0. 0 is equal to 18x minus 8 means 8 is equal to 18x. X is going to equal 4/9. Okay. So that is our, essentially, important point, and we're going to use that to split the number line into intervals. Alright, so we got 4/9 right here. Maybe for our test points, I'll choose 0 and 1. Again, no need to pick complicated test points. And we're looking at the sign of f double prime of x on those intervals. Well, f double prime of 0 is 18 times 0 minus 8. That's negative 8, which is strictly less than 0. F double prime of 1 is going to be 18 minus 8, aka 10, which is strictly greater than 0. So we see that f double prime of x is positive above 4/9, and it's negative below 4/9. Therefore, f, and let's just identify f with its graph. F is concave up on negative infinity to 4/9, and concave down, concave down on negative infinity to 4/9, and concave up on 4/9 to infinity. Because we are positive, aka concave up, for 4/9 to infinity, negative, therefore concave down on anything less than 4/9. So negative infinity to 4/9. Nice and simple problems, especially because, at least with polynomial functions, right? The more we take a derivative, the simpler the function gets, so this analysis becomes progressively less bad. Let's do another example. let's determine where g of x equal to x plus 1 divided by x squared is concave upward slash downward. Okay, well, we should take that second derivative. Start by taking first. G prime of x is equal to, I'm going to rewrite this here as x plus x to the negative second. Therefore, I can get away without trying to take the quotient rule because the quotient rule sucks. Now, just by the power rule and the sum rule, g prime of x will be 1 minus 2x to the negative third. Okay, and now g double prime of x, second derivative, will be equal to, okay, derivative of 1 is 0. So we're going to have negative 3 times negative 2 is positive 6. X to the negative 4. aka 6 divided by x to the fourth. Alright, so let's quickly note g double prime of x is undefined. At x equals 0, right? We get a classic divide by 0 error. Furthermore, g double prime of x is not equal to 0 for any x. Right? No matter what we plug in for x, it'll just be a number. If you try to solve and say, oh, 0 is equal to 6 divided by x to the fourth, you'd multiply both sides and you'd get 0 is equal to 6, which can never happen. So, g double prime of x is never 0. Okay, according to our procedure, that means we only need to divide the number line at 0. So let's do it. I'm going to choose negative 1 and 1 as my test points. And we're looking at the sign of g double prime of x. Alright, well, plugging in our test points, g double prime of negative 1 is 6 over negative 1 to the fourth power. That's just going to be 1. So we're left with 6, which is greater than 0. And here, g double prime of positive 1 is 6 divided by 1 to the fourth, which is, again, 6 divided by 1, aka 6, which is greater than 0. So, g double prime of x is positive on both sides of 0. That just means that g double prime, that means that g of x is going to be concave upwards everywhere except at 0. So concave up on negative infinity to 0, union 0 to infinity. Right? We can't say it's concave up at 0 because the second derivative doesn't even exist there. Alright, there we go. So, in fact, the actual function doesn't even exist there, so it wouldn't even make sense to talk about its concavity there anyways. Alright, so we've talked about g double prime of x is greater than 0, less than 0, intervals of concavity, that's all well and good. But what about those times when g double prime of x is equal to 0? Do we get something special there? We talked about critical points with our first derivative being equal to 0, but what about second derivative? And it turns out, we get another nifty thing. inflection points. So let's start off with an example, and then we'll go from the example and see what happens to everything else. Let's let f of x be x cubed. Okay, f prime of x is equal to 3x squared, f double prime of x is 6x. So let's note that f double prime of x equals 0 at x equals 0 and nowhere else, right? So that's all well and good, all and simple. Why do we care about this point and the second root being equal to 0 there? Well, let's graph our original function f. And the graph of f of x would look roughly like this. This is the point we're concerned about, right? This little 0 there. We see that not only is the first derivative 0 there, but this point isn't a local minimum or a local maximum. But what is going on? Well, this function is going from concave downwards to concave upwards. And somehow that has to be connected with this second derivative being equal to 0. So let's make that formal with the definition. A point on the graph of any continuous function, not necessarily differentiable, but just of a continuous function, let's call it f, where the tangent line exists and the concavity changes. Is called an inflection point. So, anywhere, for any type of function, that we see behavior that looks like this, changing from one concavity to another, we're going to say, hey, that's an inflection point, as long as it makes sense to talk about the tangent line there. So something like this, concavity does change, right? This is bending down, this is bending up, but this would be not an inflection point. Right? Because even though the concavity is changing, the tangent line does not exist there. So we want to count away points that look like that, but include things that look like that. So let's draw a couple examples that would give us inflection points. Maybe we'd have something that looks like this. We'd have an inflection point right about there, right? We're going from concave up curve, concave up kind of looks like a smiley face, to concave down, kind of looks like a frown. Or maybe you could talk about something that looks like that, right? Where we're going from concave up to concave downwards. And this actually gives us a cool picture because it shows there's two different kinds of inflection points, right? Here, there's an inflection point that looks relatively flat, so this would also be a critical point of the function. But this is an inflection point that would not be a critical point. So they are separate objects, and that's cool. So, how do you get inflection points? What are they good for? To find inflection points, it's going to be very similar to finding critical numbers, except using the second derivative. So step 1, compute the second derivative, so long as it exists. 2, we're going to find points in the domain of the function where f double prime of x equals 0, or f double prime of x does not exist. Okay? So now that we've done that, we examine the sign of f double prime of x on both sides of each number from 2. If there's a change in sign, doesn't matter which change in sign, positive to negative or negative to positive, either one gives you an inflection point. Alright, so if the f prime if f double prime of x changes sign, then c f of c is an inflection point. And you're like, hey, where the heck did that c come from? C was just the number you got in 2. So you're going to test each of those points looking on both sides of it. If the second derivative changes sign as you move across it, then the point is an inflection point. So let's confirm that x cubed does actually have an inflection point at 0. We've seen it graphically. Let's see it using our procedure. All right. Well, let's take those derivatives. F prime of x is 3x squared. F double prime of x will be 6x, just like before. And now you see, hey, let's pick some test points. 0, -1, and 1. Right? 0 is the point we care about that we're testing. -1 and 1 are our test points. F double prime of -1 would be -6, which is less than 0. f double prime of 1 is positive 6, which is greater than 0. Therefore, zero, 0 is an inflection point. Great. Let's do another example, one that we haven't seen, as I proceed to take my jacket off because it's getting warm. Let's determine